Unlike yesterday's cartoon, I think this one is very appropriate, having just finished Thanksgiving. So again, if you want to take time to read it, pause the video. Here we go. Today we look at antidifferentiation by parts. Yesterday we looked at section 6.2, antidifferentiation by substitution, which was used mainly in composite function situations. The antidifferentiation by parts is used mainly in product situations. If you have two functions being multiplied together, that does create an issue because you cannot just integrate each individual one. That's why we have integration by parts. It breaks up the integral into two separate parts. Your formula for integration by parts is right up here at the top. The integral of u dv, where again u and dv represent two functions together, is equal to uv minus the integral of v du. Now you'll notice that there's an integral answer, or an integral in the answer. What that tells me is that I'm going to take these parts here, manipulate them a bit, and then I'm going to set this up and then take the integral. So what are our guidelines? Well, first of all, when we're selecting our u and our dv, and the selection of u and dv is most crucial to the problem, try letting dv be the most complicated portion of the integral that has a basic integration rule. If you select dv's with complicated integration rules, you're going to make a mess of things. U is the remaining one. U is usually the part that the derivative will become simpler and smaller as the problem goes. For instance, I might pick x squared for u, because the derivative of x squared is 2x, the derivative of 2x is 2, the derivative of 2 is 0. You see it goes down and it becomes simpler. So here's our first problem, the integral of x cosine x. Again, I'm left with the question, what is u, what is dv? Well, u needs to be the simpler part. dv is the part that we have an integral, a very simple integral formula. Now, we have integral formulas for both of these. But if I pick x as the dv, the integral of x is x squared over 2. The integral of that becomes increasingly more complicated. But if I go the other way, if I let u equal x, then du is just 1 dx. You see it's simplified down. If I let then dv be equal to cosine x dx, and notice it's the whole part there, cosine x dx, I take the integral of both sides. Well, I know what the antiderivative of cosine is. The antiderivative of cosine is sine. It's very simple. Now I take these and I plug them into my formula. uv x sine x minus the integral of v du sine x dx. So it looks like this. And now this part is done right here, x sine x. I simply take the antiderivative of sine. The antiderivative of sine is negative cosine, and that negative along with this one will become plus, and then plus c. Sometimes you have to repeat integration by parts. You'll simplify it down to a certain point, but then it needs to be simplified further, such as this one. Now again, if I were to pick x squared as my dv, the integral of that, x cubed over 3, would just become more and more complicated. Not only that, but the e to the x, if I'm taking the derivative of that, doesn't do anything. So let's flip-flop that around and let's let u equal x squared, which means du is 2x dx. dv is e to the x dx. It's the part that's left over. Well, the integral of e to the x is e to the x. It doesn't change. uv minus the integral of v du will look like this. Now this x squared e to the x part is finished. However, this part is not, because I still cannot take the integral of e to the x times 2x. It's not a u substitution. There's no simple rule for that, so I have to do integration by parts again. Now here's the key on repeated integration by parts. Be consistent. If you let u equal your x term here, as we did, and dv equal the e term, then as we go, there's going to be an x term continued and an e term continued. The u continually needs to be the x term. The dv continually needs to be the e term. So u is going to equal 2x, which means du is 2 dx. dv is e to the x dx, and v would be e to the x. Set that up now. uv minus the integral of v du looks like this. uv minus the integral of v du. Alright, now we'll distribute our negative, and we end up with this. The integral of 2e to the x is just 2e to the x, and we're done. Don't forget this initial part, though. Sometimes a lot of people will leave off that first uv part from the first step of the integration by parts. Don't leave it off. It's crucial to the answer. Now, we can do integration by parts with the initial value problems, if you remember those, where These are the problems where we look for that c value, that plus c value. So we start out with the equation dy dx equals x natural log x, and our job is to solve the differential equation. In other words, we want to get rid of the dy dx. To do that, I'll go with the idea of differentials. I'll move the dx over here. Now to get rid of the d's, to get rid of the derivatives, I will integrate both sides. Well, the integral of dy is just y. Now we have this part right here, and we have to do integration by parts. Now, you may be thinking, well, in the past I've always let u equal x, so let's let u equal x again. Well, the problem again in there is the dv is natural log x dx. And if you remember the shortcut from that from yesterday, great. Not many people do. It is not a simple formula. So let's instead flip it around. Let's let u equal natural log. Du then would be 1 over x dx. I'll move the screen down so you can see. dv is going to be x dx, and v is x squared over 2. Now I know this one became more complicated. I know that. But this one, you see, actually simplified, and that's going to take care of the complication here. So uv minus the integral of v du would be this right here. uv integral of v du right here. X squared over 2, 1 over x can simplify to be just x, and then the over 2 part can come out to be 1/2. Now the integral of x is x squared over 2, and then when you multiply it with that over 2 that was already there, over 4. Now, the initial condition was x equals 1 when y is negative 1, or vice versa. So y is here. I plug in 1 for x there and there. Natural log of 1 is 0. That's gone. So I've got the negative 1/4 plus c. I'll move that 1/4 to the other side. C is negative 3/4. Plug that back into the answer we had previously, and there's our final answer. Alright, next problem. Solving for an unknown integral. Sometimes when you're working an integral, you get yourself into an endless loop. The integration by parts just keeps taking things back and forth. How would you recognize that that's going to happen from the beginning? Well, let's think about e to the x. What's the derivative or integral of e to the x? It stays e to the x. If we think about cosine, the derivative of cosine is sine, goes back to cosine, and it just fluctuates back and forth. So this would be one of those endless loop problems. Well, there's a neat little trick for getting out of that loop. Here's what we do. I'll let u equal cosine x, du is negative sine x, dv is e to the x dx, v is e to the x. Really, on this problem, it's irrelevant which one you pick. I could have easily flip-flopped and said let u equal e to the x, dv cosine x dx, and it would have made no difference whatsoever on this problem. And that's how it always is on these loop problems. So I'll put it together. uv minus the integral of v du would look like this. Now you may be wondering why on all of these problems I always write the problem down on the left-hand side. I've always kept the original problem written down throughout all the work, and there's a reason for that, and you're going to see that on this problem. So here I'm done with this part. I've got rid of the integral sign, but I've got a similar situation here that I had up here. I've got an e to the x, and I've got a cosine x up here and a sine x down here. What I'm going to do is I'm going to be consistent. U was cosine here, so down here u is going to be sine. So du is cosine x dx. dv will be e to the x dx, which makes v equal to e to the x. Now if I set up this part, uv minus the integral of v du, I have this. Now what I hope you notice, here's the first uv part, there's the second, but when I come to this part right here, that looks exactly like what we have over here, except for that it's negative. Well, as I have like terms here, so to speak, I'm going to take this that's a negative, and I'm going to add it over to this side, so I now have two of them. And I was solving for this right here, which means I want to get rid of the 2, so I'll divide everything by 2, and there's my final answer. Now, there is a shortcut for integration by parts. Not really a shortcut, so to speak, but a lot of people like using tables, and they think it makes this go quicker, faster, keeps it more organized. I don't know exactly, but I do know that some people prefer. So I'm going to show you the table approach to integration by parts. On the left-hand side, you have f of x and its derivatives. Now, instead of putting f of x and its derivatives, we could come over here and put u and its derivatives. G of x and its integrals, instead of g of x, we could put dv and its integrals. Now you may be wondering about these signs. It has to go in this order, plus minus, and if we have more steps, it just keeps going plus minus, plus minus. Alright, so what would the u be for this problem? Well, the u for this problem would be x squared. Now, and its derivative. So what's the derivative of x squared? 2x. The derivative of 2x is 2. The derivative of 2 is 0. And I do take this all the way down to 0. Now, the g of x, or the dv that we had a moment ago, would be what's left over. Well, that would be the e to the x dx. Or we just use e to the x for this part. And the integral of e to the x is e to the x again and again. Now, we combine these in this fashion right here. Oh, let me back up. I went one too far. Now, let me redraw the lines because this was the best I could do with these straight lines. Technically, what we're doing is this. We're starting here at x squared. We're going straight across to the positive, and then we're going down a step like that. So it's actually got a little bend in it. There to the negative and down, and then there to the positive and down. So I take x squared times the positive, so it stays x squared, e to the x. So x squared e to the x. Then the next term would be 2x times the negative, so negative 2x e to the x. And then the last term would be again be positive 2 e to the x. So that in the end, I have this answer right here. Don't forget your plus c. A lot of students last year did prefer the table method. If you like it, that's fine. Some people do, some people don't. Alright, here's one for you to try if you want. I'll go ahead and go through it. Integral of x cubed sine x dx. So again, f of x will be x cubed. That would be the u equivalent. X cubed, 3x squared. Keep taking the derivative, 6x, 6, and remember, take it all the way down to 0. Sine x would go here. The integral of sine is negative cosine. The integral of negative cosine is negative sine. Goes back to cosine, and then back to sine. Now make your lines. X cubed positive cosine negative. So it would be negative x cubed cosine x. And then that would be negative 3x squared times negative sine. So it would be positive 3x squared sine x. That would be a positive 6x and a cosine. So 6x cosine x. And then minus 6 sine x plus c. Now, last lesson, I told you that we would prove in this lesson the natural log x formula. So natural log x dx, taking the integral. I start out with letting u be natural log x. Now, it would not make sense to let dv be natural log x because the natural log x is what I'm trying to find the integral of anyway, so I don't want that to be the dv. So I let u equal natural log x, so du is going to be 1 over x dx. The dv, well, what's left over? Well, I already used natural log x. The only thing left over is the dx. So I'll put that there. So v equals x. Put them together. uv minus the integral of v du looks like this. The x and the 1 over x cancel. And then all we have here to do is the integral of dx, which is just x, and then plus c. And that was our formula from yesterday, if you want to go back and look at your notes, for the integral of natural log x. Another integral we have, the integral of the arc sine of x dx. Again, we'll let u equal arc sine x dx, or just arc sine of x. Du, the derivative of arc sine, is this. You can go back and look that up in a previous chapter if you wish. dv would be dx, v equals x. uv minus the integral of v du looks like this. We can put that together. Now this is going to be u substitution. I'm going to let u equal 1 minus x squared, which means du would be negative 2x dx. I already had the x. I needed the negative 2. So I'll put the negative 1/2 out here. That's what makes it positive. Now if we continue on, it does work out to be this, which will simplify out to here. Again, if you have any questions about this, I'll be happy to answer them tomorrow. I will tell you that I took this, once I did my substitutions, and I wrote this as u to the negative 1/2. I then added 1 to the negative 1/2 divided by the new exponent. And that is all.